Okay, folks, we're in section 7.1, applications of definite integrals, and we're working on accumulation and net change. So we just left the problem where we were talking about a pump connected to a generator operates at a varying rate depending on how much power is drawn from the generators to operate the other machinery. The rate in gallons per minute at which the pump operates is recorded periodically over 60 minutes. And you can see that we did the integral. We want to know how many gallons were pumped during that hour. So you can see that if I do the definite integral from 0 to 60, I'm going to get gallons at 60 minus the gallons at 0 would give me the number of gallons that I would gain. However, we're not working with the right-hand side of this equation. We're working with the left-hand side of the equation. So we're just saying we need that net change. So we have R of t being the rate that's in a table of values. So we're taking that table and we're using a numerical method to approximate what the integral of R of t dt would be. So I chose to use trapezoidal to approximate, and we don't have an R of t equation, but we're able to then go ahead with trapezoidal, get our final value, and I know it was kind of quick, but I just wanted to make sure that we went through this. I got 3,550 gallons are pumped in the first 60 minutes after doing the trapezoidal. So we're looking at the integrals of a rate dt, where in a case where we had a rate that was jobs per hour, remember that a summation, an integral is a summation, and it's rate times dt, which is jobs per hour times hour, which would give you the units of just jobs. So that always helped me to think, do I have the right expression here? Am I looking for the right thing? So first thing we're going to do on this next, so it'll give you a good indicator, hey, am I at least headed in the right direction here? So in the next problem, we have a gopher problem. A 10-mile stretch of a rural Minnesota road is bounded by the north by colonies of pocket gophers. Along the road, the density of the gopher population is 500 per square mile. You can see that I have that marked right here. Let me get a lighter color. So I just marked it so that I'd have some kind of note to self that right around the road, it's 500 gophers per square mile. That's a density. And then the density as you go out to 3 miles is 2,000 per square mile. Now, understand it says something really key here. The density increases linearly until it reaches 2,000 per square mile, 3 miles from the road. We want to find the total population of gophers in this stretch of land that is 10 miles long and 3 miles wide. So what I did is I took a rectangle, drew the road. So you can see the road is right along here. I'll make it a blue road. Okay, there's the road. So I drew so that I would go 3 miles away from the road on both sides. And then I drew a line where I was exactly 3 miles away from the road, and it would go from 500 square miles to 2,000 square miles. So just drawing this rectangle with regard to the information given. And then I drew a representative strip, we sometimes call it, or a rectangle. It's a representative rectangle that says that. Now, if we're looking at this, I made randomly, but I made the variable for the 0 to 3 miles, I made it y. So it's going to go up y units from 0 miles to 3 miles. And then I drew a rectangle. So if we consider that strip, this would serve as the representative strip of land that has a density of so many gophers per square mile times square miles, which, if you think about it, the density being in the number per square miles, number of gophers per square miles, and then it would be times square miles. So you can see that the information there would then be gophers, and that's what we really want. So here's how we're going to handle it. So find the total population of gophers in this stretch of land that is 10 miles long and 3 miles wide, right? So we can't consider this as a constant 3 times 10, 30 square miles, okay? Because the gopher population has a different density as we go from the bottom to the top. So what we do is we pick a representative rectangle for this. But what we're going to do first is say that if we consider, you see I have a little y sub k there. I want to find the linear relationship between, and I use population for gophers, y and p. So there's where this is the population, right? What is the linear relationship if it exists? So linearly, the first thing I'm going to look at is I've got this y and p ordered pairs, 0, 500, right? So to find the linear relationship, I first find the slope. And then after I find the slope, I write the equation. So I know that for y miles from the road going out, I know that p is 500 times y plus 500 then. Okay, so that information is there. So there is our linear relationship that we have. Now, what are the units on these? So P is going to be the population per square mile, right? So if you look at this information, you have population per square mile per, look at 30 per mile. This is actually going to be, the slope itself would be population per mile. Population per mile cubed, if you will, but we don't even want to look at that. Okay, so we've got our y and p units there. So now we lay down a representative rectangle. So we can kind of see in that representative rectangle, we're going to model the population using area. So here you see I use the units again. We want population, so population per square mile times mile squared is going to be population. We need an expression for the population in this K strip. Because remember, you've got to think about this. We have a representative strip, and wherever that is, we're going to have to use that to say, okay, that is going to be the relationship that exists in population per square miles for the population in the kth strip. Population per square mile, I mean. So then we need a population for the area. So we have the linear equation for the population per mile squared, and then we need an expression for the area, which would simply be, area would be 10 miles long times delta y miles squared. Okay, so now we have that, delta y miles squared. Then next, we need an expression for the population in the kth strip. So I have the area really, but I just need the population itself for the K strip. So remember, the population per mile squared was the P of Y, linear relationship. Then I have the expression for area, and then I want to take those two and I want to multiply them together. So we end up with this expression. This is the population for one strip then, okay? The units are population. The miles squared cancel, and we end up with just pop. All right, and then here's what we want to do. This gives you the foundation for your integral, right? It's just going to be this, right? Except you don't use the y sub k or the y sub I or whatever it is you use, and you don't use the delta y, you use the dy. So here's what we have. The population, we want to add up all of those strips. And listen, as y varies, we have that offers us that P of y equation that is going to, let me go back up to it, this one, that is going to determine what is the population density, P, given those number of miles in y away from the road. So we have the summation, we put that all together. So we have the population total is approximately equal to the Riemann sum from k is equal to 1 to n of 500 y sub k plus 500 times 10 delta y. And all I did in the next step was just distribute here. And then the limit, I'm going to take the limit of that Riemann sum, and I'm going to say it's equal to then the integral from 0 to 3 of that linear relationship 5,000y plus 5,000 dy. Integrating that from 0 to 3, I get the following answer then. I get 2,500 times y squared is 9 plus 5,000 times 3, and I get there are 37,500 gophers that will exist on that stretch okay? So now you could do some approximations, and it should make sense when you're doing the approximations. If you do rectangles that say they're going to be, I'd say probably a mile high, if I'm going to do that, 10 miles wide, and do some kind of an approximation if you wanted to, as you would use some midpoint between 5,000 per square mile and 2,000 per square mile. You could do 3 subintervals and like that. But there's your exact answer. Okay, so I'm going to stop the video and I'm going to pick up with the last problem in this set. And again, this is example number 8 in 7.1, accumulation and net change. Okay, I'll be right back.